In general relativity, we have started to discuss a very important concept of gravitational waves in our previous lecture. And in the first lecture on this subject, we have seen a brief introduction regarding the gravitational waves. Okay? And as I have told you in that very lecture, that in forthcoming videos we will see the proper theory and this different aspect of gravitational waves. So this is the second lecture on gravitational waves, in which we are going to discuss the theory of gravitational waves. It means how we can explain this type of waves, or how we can obtain the equation of this wave, what will be its solution, and what actually we get from, what informations we get from that very solution. All these things we are now going to discuss. Okay. In fact, Newton's theory of gravity has enjoyed great success in describing many aspects of our everyday life. And additionally, this theory also explains most of the motions of the celestial bodies in the universe. Okay? But general relativity corrected Newton's theory and is recognized as one of the most ingenious creations of the human mind. The laws of general relativity, though in the case of slowly moving bodies and weak gravitational field, reduced to the standard laws of Newtonian theory, which is called actually the classical limit. So you can say that in classical limit, when we talk about the weak gravitational field and slowly moving object, that is the object which is moving at a speed which speed is actually much smaller than a speed of light, then this relativistic theory of gravity proposed by Einstein, which is called general relativity, that is simply reduced to Newtonian theory, which is a classical theory. Okay, so these conditions are known as relativistic limit. Okay, classical limit. In fact, general relativity is conceptually different from Newton's theory, as it introduces the notions of space-time and its geometry. One of the basic differences of the two theories concerns the speed of propagation of any change in gravitational field. As the apple falls from the tree, we have a rearrangement of distribution of mass of the earth, and the gravitational field changes. And a distant observer with a high precision instrument will detect this change. Okay? According to Newton, the changes of the field are instantaneous. It takes no time. That is, these changes propagate with infinite speed. According to Newtonian theory, the changes in gravitational field moves with infinite speed. So it takes no time to travel from one place to another. Okay. So Newtonian theory will be correct if this statement is correct. If the changes travel with infinite speed, then Newtonian theory has no drawback. But actually, the principle of causality would break down in that very condition. The fact is that no information can travel faster than the speed of light, according to relativity principle. In Einstein's theory, there is no such ambiguity. The information of the varying gravitational field propagates with finite speed, which is actually speed of light, as a ripple in the fabric of space-time. And this ripple in fabric of space-time is nothing. These ripples are actually called the gravitational waves. Okay. In fact, the existence of gravitational waves is an immediate consequence of any relativistic theory of gravity. However, the strength and the form of the waves depend on the details of the gravitational theory. This means that the detection of gravitational waves will also serve as a test of the basic gravitational theory. Okay. When you talk about the theories of gravitational waves, definitely, as I have told in my introductory lecture, that these waves were postulated by Einstein himself when he has proposed his theory of general relativity. So definitely, when we talk about the theory of gravitational waves, you must have in your mind the basic equation of general relativity, which is called Einstein's field equation. Okay, but you know, Einstein's field equation is a strong non-linear differential equation, and if the equation is non-linear, its solution is not easy. It will be very hard to solve Einstein's equation to get the idea of gravitational waves. So mathematicians seek a technique how to solve Einstein's field equation, and for this mathematicians follow a process of linearization. We will make Einstein's field equation linear, and then its solution becomes easy and convenient. So we are talking about a particular theory which is called linearized theory of gravitational waves. Okay. So in this particular lecture, we are going to discuss the linearized theory of gravitational waves. Okay. And for this, let us assume that there is an observer who is far away from the given static mass distribution, and the space-time in which the observer, that is he or she, lives is described by a metric, G mu nu. You know it. In fact, when there will be a perturbation, any type of perturbation which will change the metric, okay, or which will change the distribution of material, which will change the distribution of matter, then the energy momentum tensor will get changed. This T mu nu, this is called energy momentum tensor, or this is also called material energy tensor. So due to the external perturbation, there will be a change in distribution of mass or matter, and that will lead to a change in this material energy tensor. Okay. And the change in this material energy tensor actually induces a change in the gravitational field. And this change in gravitational field will be recorded as a change in the metric. Okay. So due to the external perturbation, what will happen? This will change the value of metric G mu nu, and the change in G mu nu will change the energy stress tensor T mu nu, and this change in T mu nu will induce a change in the gravitational field, and this change in gravitational field will lead to a change in the metric. Okay. So in the presence of the external perturbation, the metric G mu nu will get changed. So if you consider that this G mu nu tidal, I have made a symbol over this G mu nu in LHS, you can see this is just called tidal. So G mu nu, this is the value of this metric in presence of the external perturbation, and that will be equal to the original G mu nu when there was no external perturbation plus H mu nu. This is change in this metric. So this H mu nu is actually a tensor which describes the variation induced in the space-time metric G mu nu. In fact, we will see later on that this H mu nu describes the propagation of the ripples in a space-time curvature. In other words, we can also say that this h mu nu causes the gravitational waves. Okay, gravitational waves. So as I have told you earlier that we are going to see the linearized theory of gravitational waves, which is caused due to the change in gravitational field due to any change in mass distribution. And the basic equation which will be actually utilized to find the idea of a gravitational wave, that will be Einstein's field equation. Okay, and this quantity h mu nu, or this tensor h mu nu, you can say, as I have told you, this can be used to describe the gravitational waves. So first of all, we are going to calculate or compute this h mu nu. And if your aim is to calculate this tensor h mu nu, definitely you have to solve the Einstein's field equations. And what are Einstein's field equations? We have already discussed in very detail in our previous lectures. You know, this is given as g mu nu equal to 8 pi g over c4 times t mu nu. Okay, where you know this g mu nu is the Einstein tensor. Okay, capital G in RHS is actually universal gravitational constant, c is speed of light. Okay, and this T mu nu is the energy stress tensor. Okay, and as I have told you earlier that these Einstein's field equations are highly non-linear, and therefore their exact solutions are very hard to obtain. Okay, so definitely if your aim is to obtain its solution, you have to follow a mathematical trick or technique. First of all, we will make these equations linear so that their solution will become easier. Okay, and you know, when we talk about a region where there is a weak gravity, and where will be weak gravity? The region which is far apart from the strong sources like black holes or neutron stars. If the region of calculation is far apart from the source of gravity, which is although strong, but our calculation point is very distant from that, then there will be a weak gravitational field. And in a weak gravitational field, you have studied earlier that the metric is nearly flat. It means Einstein's theory becomes almost Newtonian theory. Okay. So in this condition, we can treat the gravity as a small perturbation. Gravity will be now treated like a small perturbation of Minkowski spacetime. It means we will say that the space-time is flat, that is the of the Euclidean geometry or Minkowski space-time, and the weak gravitational field just acts like a perturbation. As we have studied the perturbation theory in quantum mechanics, we talk about the unperturbed Hamiltonian, and when there is a weak perturbation, the Hamiltonian gets slightly changed. So we will consider that our space-time is flat, but there is a small perturbation, and what is that perturbation? That perturbation is gravity, and that will actually make a difference in the space-time. Okay. So if your aim is now to write the space-time metric, then you can write it as a perturbation of the Minkowski metric. Okay, you know this eta mu nu, this is Minkowski metric. Okay, and g mu nu is the new metric. Okay, which has been actually occurred when there is a small perturbation, which is actually gravity in the present case, that is h mu nu. So G mu nu is equal to the unperturbed metric eta mu nu and plus the perturbation term h mu nu. Here h mu nu is the perturbation. But as we have taken the perturbation very small, very weak, so definitely the magnitude or the modulus of this h mu nu must be very less than 1. Okay. So it is convenient but powerful way to proceed, namely to assume that this modulus of h mu nu must be much smaller than 1, so that we need only keep terms linear in this h mu nu in our calculations. Okay. Actually, in making this approximation, we are effectively assuming that the that the disturbances produced in the space-time are not huge. This perturbation is very small. This linearization approach has proved extremely useful for calculations, and for weak fields at least gives accurate results for the generation of the waves and for their propagation. Okay. In fact, the first attempt to prove that in general relativity, gravitational perturbations propagate as waves with a speed of light is due to Einstein himself. Shortly after the formulation of his theory, he proved that by assuming linearized perturbations around a flat metric, that is, Einstein proved it simply by taking G mu nu is almost equal to eta mu nu. Okay. In this limiting condition, Einstein proved that the gravitational perturbation travels as a wave, which is called gravitational waves, and the speed of propagation is equal to speed of light in free space, that is equal to c. Okay. And as I have told you that this eta mu nu is the space time for the flat, this is this represents the flat space time, okay, or the space time defined by Newtonian theory. And actually this is a 4 by 4 matrix and a diagonal matrix. Its diagonal elements are these. Actually, in my previous lectures I have defined it like 1, 1, 1 and minus 1. But both are same. When you take the fourth coordinate time as the 0th coordinate, then we write like this. And when you consider it as this is first component, this is second, this is third, and this is fourth, time as a fourth coordinate, then this is written like this. So both are correct. Okay. And as I have told you that this h mu nu is the small perturbation representing the gravitational field. Okay. Now we only keep terms linear in h mu nu. Okay. Discarding higher order nonlinear terms, so that the Einstein field equation will become linear and its solution will be easier. Okay. So now we are going to see what is the linear form of Einstein's field equations. And as you can see that in the Einstein field equation contains two tensors, G mu nu, which is called Einstein tensor, T mu nu, which is energy momentum tensor. And actually Einstein tensor is defined in terms of the Ricci tensor. Okay. And that is defined in terms of Christoffel symbols. So definitely we will have to write the expression for the Christoffel symbol and the Ricci tensor in linear form. So now let us expand the Christoffel symbols to first order only. In first order, the Christoffel symbol is written as gamma rho mu nu equal to 1 over 2 eta rho sigma. This del rho h nu sigma plus del nu h rho sigma minus del sigma h mu nu. In fact, here when you write del rho or del nu or what does it? Actually this is does the partial derivative. This is del x rho. Okay, this is the partial derivative operator. And the linearized Ricci tensor R mu nu, this is defined like this. Okay, here actually there is a symbol here which is called box symbol. What is this and how it is defined and what is this h? Let us see. In fact, h is h rho rho. It means this is actually the trace of h mu nu. Okay, this is trace of h mu nu, and this box symbol actually represents this much: eta rho nu del rho del sigma. Okay, for this we have written this box symbol. Now when we will use these two linear forms of Ricci tensor and the Christoffel symbol in Einstein's tensor expression, then this g mu nu is equal to r mu nu minus 1 over 2 eta nu r. Here r this is called Ricci scalar, or this is the Ricci scalar curvature. Okay, and in that condition Einstein's field equation becomes linear, and it is given as this box operated on h mu nu equal to minus 16 pi g over c4 times t mu nu. Okay, I have actually skipped some of the mathematical steps for simplicity, because that will be a tedious task for you, and for writing answer in your examination that is not needed. Okay, so this is the linear Einstein's field equations. Okay, actually here we have introduced the trace reversed perturbation, that is h mu nu tidal is equal to h mu nu minus this much 1 over 2 eta mu nu h. Okay, now if your aim is to write down this Einstein's field equations in free space, then definitely you will have to talk about the gauge condition. Okay, so here we will talk about gauge freedom and Lorentz gauge. Actually, in the linearized theory, an infinite infinitesimal coordinate transformation, like when your aim is to transform the coordinates x mu to x dash mu, then how it is carried on? This transformation is carried on x dash mu is equal to x mu plus this zeta dash mu of x. Okay. So if we consider such an infinitesimal coordinate transformation, then the change in perturbation will be what? Under this type of coordinate transformation. So if you consider that this h mu nu changes to h dash mu nu, then this h dash mu nu under this type of coordinate transformation is given as h mu nu minus del mu zeta nu minus del nu zeta mu. Okay. In fact, this result is used to impose the Lorentz gauge, and that Lorentz gauge is just given like this: del mu h mu nu equal to 0. In fact, this condition is also called, in fact, a Hilbert gauge condition, which is just equivalent to Lorentz gauge condition of electromagnetism. So I have used the term Lorentz gauge here. Okay. Now, you can write the Einstein field equation in a region where there is no matter. That is, if you are talking about vacuum or free space, then what will be Einstein's field equation? This T mu nu, which is called actually the energy momentum tensor. In absence of any matter, this material tensor vanishes. This is 0. Okay. So this equation which you have written here in equation number 3, this is linearized Einstein's equations. If T mu nu is 0 in vacuum, then in vacuum these equations are given by this expression. Okay. And this is actually the wave equation of the gravitational waves. Okay. This is wave equation of the gravitational waves. In fact, this box symbol is also given like this. This is del square sorry, not plus but minus del square minus del 2 by del t square. Okay, del 2 by del t square. This is also called D'Alembert operator. And you know the standard wave equation is del 2 psi minus del 2 psi by del t square is equal to 0. Okay. So this is nothing, this is simply, you can say this is del square h mu nu minus del 2 h mu nu by del t square, and this equals 0. And this is just the standard classical wave equation. So I have mentioned here that this is just a wave equation. Okay. So you can say that this perturbation h mu nu, this just acts like a wave function. As in case of electromagnetic wave, you know, electric field vector and magnetic field vector propagates like a wave. Okay. Just like that, here, this perturbation h mu nu propagate just like a wave traveling at a speed of light c. Okay. And therefore, now you can easily write what will be the plane wave solutions of this wave equation. So this is a very remarkable equation. This is the classical wave equation of gravitational wave, and its plane wave solutions are given by this expression. This is h tidal mu nu of x equal to h a mu nu e to the power I k rho x rho. Here actually this k rho mu is the wave vector, and this wave vector satisfies this condition. K mu times k superscript mu, kappa superscript mu times kappa. This is 0. It means the scalar product of the two wave vectors, one is contravariant and another is covariant, that is 0. It means this is just a null vector. Okay. And so it is just like light. And this result actually implies that the gravitational wave is a transverse wave traveling at a speed of c. So this is a very remarkable fact, and this result actually shows that you can also say like this kappa mu times kappa mu equal to 0. So this result implies that gravitational wave is a transverse wave. This is a very important property of gravitational wave. Just like electromagnetic wave in free space, you know, is a transverse wave. Simply in free space, gravitational wave is also a transverse wave. Okay. Now, for knowing some extra other properties of this gravitational wave, we are talking about transverse traceless gauge, TT gauge. In fact, I have not derived these results, but I have mentioned here some facts, and you should remember it. Okay, so that you can easily write the answer of your question in your examination. Actually, in TT gauge, we see that H0 mu, this is equal to 0. It means there will be no time component, okay, in TT gauge. And del I operated on Hij, that is also 0, which shows that this wave is a transverse wave, and Hii is 0, it means it is traceless. So you can conclude that the gravitational waves has only two independent polarization states. Okay, only two independent polarization states remain in this gravitational wave. And for a wave traveling in z direction, this h tt mu nu, it means you are now going to write the value of h mu nu if the wave is traveling in z direction in traceless transverse traceless gauge. Okay, and that is given by this matrix, you can see. And here this symbol H plus, this is called plus polarization. It means this stretches space along x direction while compressing along y direction, and vice versa. It means this also implies that it stretches the space along y direction and compresses along x direction. And another polarization state is denoted by H cross. This is called cross polarization, and this its effect is same as rotated by 45 degree. Okay, so this is called cross polarization. Now we will see the energy of gravitational waves and its detection, when it will be detected. Okay, although I will provide a detailed lecture on detection of polarization of gravitational wave, but here we will only see when this wave will be detected. Okay. Again, I am telling you that I have not derived the result for the effective stress energy tensor for gravitational wave, but I have mentioned it directly, so you should remember it. Okay. As I have told you earlier, that this h mu nu is very small. Okay. When we use LIGO sources, we will talk about LIGO sources in our forthcoming video, then it is seen that the value of this h mu nu is almost 10 to the almost of the order of 10 to the power minus 21. Okay. Okay, so this is very small. Although the value of h mu nu is negligibly small, in spite of that, we say that gravitational waves carry energy and momentum. You can't say that it does not carry energy and momentum. And the effective stress energy tensor for gravitational waves is given by this expression. You should remember it. Here the superscript GW refers actually gravitational waves. So this is energy stress tensor for the gravitational wave, and this is given by this expression. Okay. In fact, this gravitational waves are how generated. You know that the electromagnetic wave is generated by the accelerated charged particle. It is also produced by the accelerated dipoles, which is also called oscillating dipoles. So even a point charge which is in accelerated motion, that produces electromagnetic wave. An oscillating dipole also produces electromagnetic wave. But when you talk about the gravitational waves, that is not produced, or that is not generated by a monopole, that is a point mass, or it is not produced even by the dipole radiation. Okay, because the dipole radiation is forbidden in this case due to the momentum conservation. In fact, Gravitational waves are generated only by time varying quadrupole moments of mass distribution. This is a very remarkable fact. I have mentioned this fact, I have not explained it. But in our forthcoming video, I will try to explain how we can say that gravitational waves are generated by the time dependent quadrupole moments of mass distribution, not by dipole radiation. So remember it that gravitational waves are generated by time dependent or time varying quadrupole moments of the mass distribution. And this is the reason that only the sources like binary neutron stars, black hole merges, and supernova are the strongest source of gravitational waves. A mere point mass is not a source of gravitational waves. The waves produced by such a mass will be so weak that this energy stress tensor will have such a smaller value that can be neglected. Okay. So this wave is experienced, this wave is actually detected when our source is very strong, whose quadrupole moment of the mass distribution of the source varies with time. Only then this wave is produced and detected. Okay. So this is all about the linear theory of gravitational waves. I have mentioned here some of the remarkable fact for the objective type of question. When you talk about gravitational waves, you can say that in free space such a waves are transverse in nature, like electromagnetic wave. These are traceless and massless spin 2 excitations. It means when we talk about the quantum theory of radiation, then we say that gravitational waves correspond to the quanta, which is called gravitons, and these gravitons are massless spin 2 particle. You know, photon has spin 1, but gravitons has spin 2 and 2 polarization states also. Okay. So gravitons are massless particle having 2 spin states or having spin 2 uh, and these waves are traceless and transverse. Okay. So this is all about the linearized theory of gravitational waves, and I hope you have definitely enjoyed this lecture. Okay, thank you very much.